Okay, so today I've chosen or selected three different problems to give you an idea of the process that you move through to complete these combined loading problems. And the combined loading problems are really the first point in the course where we take all of the material that you've learned to date and sort of roll it up into one complete problem. So the problems are going to touch on concepts that you've learned throughout the entire course so far. And it's going to continue to be that way through this last third of the course. After we complete combined loading, we move on to stress transformation, which is adding another layer onto combined loading, and then failure theories, which is adding another layer onto that. So three problems again, and these are a little bit longer problems now. So let me put the first one up on the board here. So we've got a gear here. Let's make it a little bit three-dimensional like that. And we've got a shaft coming out like this. And this is fixed to rigidly fixed like that. And then we've got some forces being applied at this location here. And what have we got? We have got a force in this direction. That's 125 pounds. We've got one along the direction of the shaft. That's 75 pounds. And we've got a force that's acting vertically downwards that is 200 pounds here. And the diameter of this shaft is 1 inch. Okay. And there is a location of interest here that is part of the way along the shaft. So if we draw a section plane within that shaft and draw some lines like this. There, our point of interest is on the circumference back there, and we'll label that point A. Okay. So the question statement says, the A36 steel shaft has a diameter of 1 inch. Define the stress state within the shaft at location A using a volumetric element. So I'm just going to write that down and then we'll talk about what that problem statement actually means. So define stress state at A using a volumetric element. Okay. So, first of all, volumetric element. What this is referring to is a representation, a three-dimensional representation of the little bit of material that exists at point A. So I'm going to draw the little bit of material that exists at point A in 3 dimensions here. So point A is going to be a little cube of material that looks like this here. And we'll put the hidden lines in like that. Okay. So this cube of material is the material that's located at point A. And point A is right on the circumference of the shaft. So to sort of orient you between this element and that picture here, This left-hand surface of the cube, that is on the outside surface of the shaft, and the rest of the cube of material is coming into the actual body of the shaft. So this here is the outside surface of the shaft. There. Okay, so that's the volumetric element at point A. So defining the stress state means to identify all the stresses that are present at A and place them as vector representations on this volumetric element. Okay, so we need to identify all of the normal stresses and shear stresses that are at point A, what their directions are, and choose which faces of this volumetric element they act on, place them there in their correct directions, and find their magnitudes. Okay, so that is defining the stress state at A using a volumetric element. Okay, so there's sort of a systematic way to go through a problem like this, and we're gonna practice it using this problem, and then we'll do another problem that's very similar to this one, and you'll see the process get repeated again. So the first thing to do when you have a problem like this is, if you want the stresses at point A, then you need the internal forces, moments, torques occurring in the section plane of point A. So we're going to take a section cut through the shaft in the plane of point A, and then figure out what our internal forces, moments, torques are using our equations of statics. So I'm just going to erase the rest of the shaft here to turn this into a free body diagram, making a section cut through there like that. And then what you want to do is you want to stick a coordinate system on the shaft in the plane of the section cut, centered at the centroid of that cross section. Okay, so I've basically already got that done. I'm just going to extend that a little bit, and we'll erase a couple of these lines here so that we only have the positive orientation of these axes shown. So I'm going to make this axis coming out this way my x-axis. I'm going to make this one up here my y-axis. And then once you've determined what you want to choose as your x-axis and your y-axis, the positive direction of your z-axis is given by the right-hand rule, where you point your fingers in the direction of x, flip them into the direction of y, and your thumb points in the positive z direction. So that's down this way. So that's the positive z direction for my coordinate system that I've set up. The next thing that you want to do is actually draw the picture of your volumetric element, which we've already done, and then take your coordinate system and just transfer it down here beside your volumetric element so that you can keep track of the directions both that are present here and down here beside your volumetric element. So I'm just going to transfer that coordinate system down here so I know which are my x, y, z directions in relation to the volumetric element. Okay, so the next step is finding those internal forces, torques, moments. When you're dealing in 3 dimensions like this, you have 6 equations of statics that you need to pay attention to. So I like to just write them all down and then go through them one by one. So we're going to do sum of the forces in the x direction equals 0, sum of the forces in the y direction equals 0, sum of the forces in the z direction equals 0, sum of the moments about the x-axis equals 0, sum of the moments about the y-axis equals 0, and sum of the moments about the z-axis is equal to 0 too. So this object, if it's static, it needs to conform to all of these equations, or all of these equations have to be true. Now, what you want to do after you've got these 6 written down is look at your equations for the moments and figure out which you've written incorrectly, because one of these should be some of the torques. Now, the difference between a moment and a torque, both a moment and a torque are force times a distance, but moments, as you know, internal moments cause normal stress, whereas internal torques cause shear stress. And shear stress and normal stress are fundamentally different. So it's important to correctly label the force that exists, or the internal moments and torques correctly, labeling moments, and torques. All right, so in this case, the longitudinal axis of this shaft is the z-axis, so this should not be some of the moments about the z-axis, it should be some of the torques about the z-axis, since any internal things that occur around the z-axis are twisting the shaft, and that's a torque that's going to cause shear stress, not acting to bend, which is an internal moment. Okay, so going up to some of the forces in the x direction. Here you just want to look at your applied loads and think about what you need to have for reactions or internal forces in order to balance those out. So we've got one force in the negative x direction that's 125, so we need to have 125 pounds in that direction. Now that internal force that I've just drawn is parallel to the section cut that I've made, which makes this an internal shear force. So I'm going to label this as V subscript x for the internal shear force in the x direction. Okay, so we've done that equation now. Some of the forces in the y direction. We do have an applied force in the y direction, and assuming that the weight of these components is negligible, and we haven't been told specifically that we should include them, and we know that in our material property table, even though this is A36 steel, we don't have a density or specific weight for A36 steel. So we'll assume that the weight is negligible, which is a good assumption, given that it's a 1-inch shaft and the load is 200 pounds. So this, and I didn't write the length on here, which I should have. So the distance between the point of force application and this section that we're taking is 8 inches here. So 8 inches of a 1-inch steel shaft is not going to weigh anywhere near 200 pounds. So the assumption that this is weight is negligible is good. So for the force, internal force here, it needs to have a magnitude of 200 pounds. That force is also parallel to the cut section, so it's also a shear force. So shear force V subscript y in this case is 200. Okay. For the z direction, what do we have? We've got 75 pounds in that direction, so we need to have 75 pounds in this direction. And now that internal force is perpendicular to the cut section, so this is a normal force in the z direction, which is 75. Okay, so we've done these two. So let's move on to our moments and then torques next. So for some of the moments about the x-axis, what you want to do here is think about the x-axis and whether or not each of these externally applied loads creates a moment about that axis. So remember that for a force to create a moment about the axis, the projection of, or the directionality of the force and the directionality of the axis need to be perpendicular, and the projection of the axis and the projection of the line of action of the force can't cross each other in three-dimensional space. Okay, so for the 125-pound load, that's parallel to the x-axis, so it's not going to create a moment about the x-axis. the 75-pound load, if you project the line of action of that force forward, it will intersect the x-axis. So that doesn't create a moment as well. But the 200-pound load, the line of action of that force up and down never crosses the x-axis if you project the x-axis back and forward. They're always a minimum of 8 inches apart, those two lines in three-dimensional space. So 200 pounds is going to create a moment about the x-axis. It's going to act to rotate the whole object under the x-axis like that. So your internal moment needs to be pulling the object back over the x-axis in the opposite direction. So we've got m subscript x here. And we can figure out the value of that. It's going to be, let's see, m subscript x is going to be equal to this force 200 multiplied by the moment arm, which is 8 inches, which gives us 1,600 pound inches. So 1,600 there. Okay. All right, let's do the same thing for the y-axis. So here's the y-axis going up and down like that. 200 pounds is parallel to the y-axis, so not going to create a moment. The 125-pound load is going to want to rotate the object around in that direction. So we've got 125 pounds multiplied by an 8-inch moment arm. Also, the 75-pound load, it is perpendicular to the y-axis, and the two are a distance apart. And here I can see I forgot another dimension on the drawing here that I should have put on. So this distance from the edge of that gear to the center location is 3 inches. Okay, so the 75-pound load doesn't cross the y-axis in three-dimensional space. If you take the line of action and then the y-axis, they're always a minimum of 3 inches apart. Now, that's going to create a moment about the y-axis in the opposite direction. So looking at the relative magnitudes of the moment created by 75 pounds and 125 pounds, 125 multiplied by 8 is going to be a lot bigger than 75 multiplied by 3. So the net moment is going to be in the direction of the 125 pound load. So we're going to need an internal moment in the opposite direction. Okay, so this is m subscript y. And let's figure out the value of that. So m subscript y is going to be 125 multiplied by 8 subtract 75 multiplied by 3. Okay. And that gave me, what did that give me when I did it? 775 pound inches. Inches. Okay, there we go. So 775. All right, and the torque's about the z-axis. Okay, 75 pound load is parallel to the z-axis, so it doesn't create a torque. The 125 pound load, if you project that forward and you project the z-axis this way, they would cross each other right in the center of the gear there. So 125 pound load does not create a torque about the z-axis. The 200 pound load, however, would want to rotate the gear in the clockwise direction about the z-axis. So there needs to be an internal torque in the opposite direction. Okay, so this here is T subscript Z, and its value is 200 multiplied by 3. Okay, so T subscript Z here is 200 multiplied by 3, 600 pound inches. Okay, let's put that up here, 600 pound inches. Okay, so I'm transferring all of these up here because I know I'm going to want the rest of this space to keep working. So what we're going to do now is just do some erasing. up here, and then the next part, or the next step in the problem, is to go through all of those internal forces, moments, torques that we've identified one by one and figure out whether they create stress at point A, and if so, what type of stress, and what the direction and magnitude of that stress is. Okay, so there we go. All right. So let's work through the internal forces, moments, torques in the same order, going X, Y, Z for the forces and then X, Y, Z for the moments, torques. So for our x-axis, okay, what have we got here? We've got a shear force in the x direction, Vx equals 125 pounds. So the question is, let's think about whether that creates stress at point A. So I'm just going to do a two-dimensional sketch of the cross-section at point A here so we can look more clearly at the effect of that internal shear force over the cross-section. So if I do that, we've got our x-axis, just to orient you between this two-dimensional drawing and this three-dimensional drawing. My x-axis is going out that way. My y-axis is going up, so I'm sort of looking at the cross-section through the shaft here. Point A is over there, and our internal shear force Vx is acting in that direction there. Okay. So when you're calculating, we know that internal shear forces cause shear stresses. And we calculate these using our equation tau equals VQ over IT. And we know that when you want to calculate the shear stress at any point, right, what you do is draw a line through the point of interest that is perpendicular to the direction of your internal shear force, and then all the points in the cross-section along that line that you've drawn share the same shear stress. And for area A prime, that's part of Q, you take the area on one side or the other side of the line that you've drawn through the cross-section, right? So we want the stress resulting at point A from Vx. So if we drew a line through point A, right, it's right there, and the value of Q, right, is 0, because either the area A prime on the left of that line is 0, or if you take the area A prime to be on the other side of that line, then you've got the whole cross-sectional area, in which case y bar prime is 0. And we've talked about that before, thinking about plotting a plot of how shear stress varies over position in the cross-section for a situation like this, where you've got 0 shear stress at the edges, and then shear stress increases to reach a maximum value at the location of the centroid. Okay. So no tau at A from Vx, because Q is 0. So the value of Q is 0 in the equation VQ over IT. Okay, let's move on to the y-axis. So to explore the effect of our internal shear force V subscript y, we'll draw a similar picture and look at exactly the same, from the same perspective here. And in this case, our internal shear force is acting vertically upward over that cross-section. So we've got Vy there. So for a shear force directed like that, we want the stress at point A. If we wanted the shear stress at point A, we'd be drawing a line through the cross-section passing through point A, a line that is oriented perpendicular to our shear force. So this line, like that, and area A prime would be the area on one side or the other side of that line we've drawn. So there's area A prime. And then y bar prime is the distance between the centroid of A prime and the centroid of our whole cross section. y bar prime. Okay. So all points on that line that I've drawn will experience a shear stress that is directed in the direction of Vy. So over at point A, we'd have a shear stress that is oriented in the direction of Vy. Okay. And similarly, any point along this line would have a shear stress that's of the same magnitude and in the same direction. So before we calculate what the magnitude of tau Vy is, let's place that shear stress on our volumetric element. So the first thing to do before you start putting stresses on your volumetric element is to look at your volumetric element and identify which face of the element is in the section plane that you've drawn. Okay. In this case, the face that is in the section plane is the back face of the element here, the one that I'm outlining. Okay. So the back face of this element is in the section plane that I've cut, and then the rest of the element projects forward into the body of the shaft. So if I just to make sure you've got yourself oriented correctly, I'll draw a larger version of that cross section over here, just to show you how the volumetric element kind of sits within the cross section here. This. Okay, there's my shaft, and point A is over here. Here's point A, but point A, we're saying we're representing it by a cube of material, and that cube of material is going to look like this. Okay, there's our cube of material that is point A. Okay, so the face that I've shaded or outlined, right, which is the back face here, that back face of the element of material is sitting right in the section plane that we've cut to expose point A. So that's important because all of these internal forces and moments that we've drawn, they act on this plane of the volumetric element that's present at A. So all of the stresses resulting from these internal forces act on that face of the element. So that's where we're going to place them. Okay. So what we want to do is we want to place a shear stress on the face of the element that's in the section plane of A, so the back face. And to do that, all we need to do is draw a shear stress on that face that is in the positive y direction. So this is why you want to have these axes right here, because looking at this, you can place a shear stress on this back face, okay, that is in the positive y direction, and this is tau Vy. Okay. Remember that whenever you're placing shear stresses on a volumetric element, they're always parallel to the face, or the face of the element that you're positioning them on. Normal stresses are always perpendicular to the face of the element. Okay. Now, when we put one shear stress on, we need to have an equal and opposite shear stress on the front face, like this, because we know that a stress multiplied by an area that it's acting over will create a force, and we need to have that force balanced if the piece of material is in static equilibrium. So if we've got tau Vy there, we need to have equal and opposite there. And then that creates a force couple which wants to rotate this element about the x-axis. So we need to have an equal and opposite pair of stresses on the top and bottom, creating a counteracting moment around the x-axis. So we also need to have a shear stress on the top face there and on the bottom face there. Okay. So whenever you place one shear stress on an element, you need to have 3 other shear stresses. So the shear stresses always need to occur in sets of 4. All right. Let's go on then to our z-axis. Any questions about the shear portion here? Okay. Let's go on to the z-axis then. So we've got a normal force along the z-axis. So to see how that force is acting on our cut section, I think it's helpful to look down the y-axis at the object from above. So we've got our cut section like this, and then the rest of the shafts in that direction. If I'm looking at it down the y-axis, then my x-axis is poking out over this way, and my z-axis is in that direction there, and my normal force NZ is oriented like this. Okay. Now, an internal normal force, that's going to create a normal stress. This internal normal force is pressing in on the cut section, so that's a compressive normal stress. So at point A, which is over here, that point is going to be under a compressive normal stress, just like all the other points in the cross section. So every point in this cross section is going to be experiencing sigma NZ, a normal stress due to internal normal force NZ. And that would be true for any other point in the cross section as well. Okay. So again, when you've got things looking like this and you've got your coordinate system here, it makes it really easy to position sigma NZ appropriately on your volumetric element. So what you want to do is go to your volumetric element, and on the face of the element that's in the section plane, so the back face, just position a compressive normal stress. So a compressive normal stress has to be a stress oriented perpendicular to that plane and pushing in on it like this. Okay, so this is sigma NZ. And then we'll again have that's not a very parallel line there. We'll have an equal and opposite one pushing on the other side. Well, that wasn't much better either. Okay, let's go somewhere in between those. There we go. An equal and opposite one on the front face. Okay. Now let's calculate the magnitudes of both of these. So let's start with tau Vy. Tau Vy is going to be given by Vq over It here. What is our shear force? Our shear force is Vy, which is 200 pounds. Q, A prime, that's the area of a semicircle, so pi over 4d squared for the area of the circle, so pi over 8d squared for the area of the semicircle, pi over 8d squared. So this is our A prime there. Now for our Y bar prime, which is the distance between the centroid of the whole cross section and the centroid of A prime, what we really are finding there is just the centroid location of a semicircle. And the centroid location of a semicircle, Y bar, is always located 4r over 3 pi from the base, where r is here the radius of that semicircle. So that's equivalent to 4d over 6 pi. Okay? And that's something that would be in the back of your textbook. Okay, so let's use 4d over 6 pi since we have diameter here. So we've got 4d over 6 pi, and this is y bar prime there. And then we're dividing that by IT. I for a circle, pi over 64, diameter to the 4th power. And then T is the length of the line that you're calculating the shear stress along. So in this case, that's also the diameter. So we've got 1 there as well. So let me see what that number came out to be when I did the calculation. So for me, it came out to be 339.5 psi. 339.5 psi. Okay. So we're going to take that and put that over here. So we've got 339.5. And just remember that that's in psi there. Okay, let's calculate the value of sigma nz. Normal stress from an internal normal force is easy. It's just n over a. Internal normal force, in this case, nz is 75 pounds. And the area that it acts over is the cross-sectional area of the shaft, so pi over 4d squared. And that, for me, came out to be 95.5 psi. Oops. 5 psi. There we go. Okay, 95.5. All right. So we've done all of our internal forces. Now we'll go on and we'll go through again, but doing our internal moments and torques. So let's do a little bit of erasing here. Okay, that's good enough to get us started. So we'll go X, Y, Z again, starting with the moment about the x-axis. For moments, if you find it helpful to do these little two-dimensional sketches to see the direction of the stress that's created at your point of interest, which I think it is when you're starting off, then for your moments, the most helpful two-dimensional view to draw is looking down the axis that the moment is acting about. So we'll look at the object down the x-axis, and if we did that, we'd see our cut section like this with our z-axis going back this way and our y-axis going upwards. And point A is located right in the center there, and mx is occurring around the x-axis, which is pointing out of the plane of the glass in this direction, mx. We know that internal moments cause normal stress by the equation my over I. And what this moment mx is going to do is it's going to rotate the cross-section about its centroid in the direction of the moment. So we're going to have the bottom of the cross-section that gets pushed in, compressive stress, the top of the cross-section gets pulled out, tensile stress, and there's going to be a linear transition between those. At point A, there is going to be no normal stress created by internal moment mx because point A lies on the neutral axis of bending for mx. Okay? So no stress at A from mx, because A is on the neutral axis of bending for mx. Okay. So we don't need to worry about that one. Let's go on and do the moment about the y-axis. So here's our moment about the y-axis. So again, a two-dimensional sketch looking down the y-axis here. Okay. So our object would appear like this. If I look down the y-axis with our z-axis like this, our x-axis going out like that, point A is over here, and the directionality of my is like this. There's my. So again, my is taking this cross-section and rotating it in the direction of my. So it's taking point A and pushing it into the cross-section. It's taking the other side and pulling it out, and a linear transition between the two. So there's going to be a compressive normal stress at point A from my. So let's place that on our volumetric element. So we just go to the face of the volumetric element that's in the section plane and add a compressive normal stress. That's a normal stress that is acting to push that plane inward. Okay, so there we go. So this is sigma my. Okay, and then another normal stress to balance that out. Okay. All right, we're on to, actually, let's calculate the magnitude of that while we're at it. I always like to place the stress visually on the element and then calculate its magnitude. So let's calculate the magnitude. So sigma my is going to be given by my over I. Okay, the value of my was 775. That was in pound inches. So 775, so we don't need to do any unit conversion since it's already in pound inches. Distance y here, that's the distance between your point of interest and the centroidal axis of bending, or the axis that the moment's acting about. So that's half the diameter. So we've got 1/2 there, and then I about the z axis coming out of the plane of the board. I about any axis, any centroidal axis for a circle is the same. So we've got pi over 64 d to the 4th power. Okay, the value of that, I've got 7.9 KSI written down, but we've been dealing with PSI, so let's look at what that is as a non-decimal value in PSI. So we've got 775 times 64 divided by 2 pi. 7,894. 7,894 PSI. Okay. 7,894. There we go. All right, one final one to do, and that is the torque about the z-axis. Okay, again, look at the object or cross section down the z-axis, since we've got something that's occurring about the z-axis. So looking down the z-axis there, our cross section is looking like this with point A there, and the x-axis coming out this way, y-axis upward like that. And what direction is TZ in? It's occurring around in this direction. So our internal torque T subscript Z is like that. Okay, internal torques cause shear stress. Tau equals T rho over J. At any point in the cross section, the shear stress is going to be in the direction of the torque, tangent to the circumference, or perpendicular to a radial line that's passing from the center outwards through the point of interest, right? So if we take any radial line, let's say a radial line like that, then any point along this radial line would have a shear stress that is acting perpendicular to that line in the direction of TZ. And we know the magnitude of that shear stress will decrease moving towards the center as a variable rho in this equation decreases. So there's the distribution of shear stress along this radial line there. So over at point A, we're going to have a shear stress that is oriented like this. So this is going to be tau TZ. So we've got a shear stress in the negative y direction. So just hop over to your volumetric element. There's the y-axis, so you want a shear stress that's in the negative y direction. So just place one on like this. So this is here, I'll just bring this out here. This is tau TZ. Okay, and if we've got one that's going down on the back face, then we need one that's upward on the front face, and then one on the top face like this, and one on the bottom face like that. The top and the bottom, those are called the complementary shear stresses, because they complement the force couple that's created by the one on the back face and the one on the front face. Okay, let's calculate the value of tau TZ. So we know what our internal torque is. It is 600 pound-inches. 600 pound-inches. Variable rho, that's the distance that your point of interest is away from the axis that the torque's acting about. So again, that is half the diameter, ½ inch. J, pi over 2 radius to the 4th power. Pi over 2 radius to the 4th power. Okay, let's see what that came out to be. 3,056 psi. 3,056 psi. Great. Okay, let's position that over here, 3,056. Great. So now we've got all of our stresses placed on our volumetric element. The only thing that we have left to do is redraw that volumetric element and combine any stresses that can be combined, and then label all of the stresses with their appropriate notations for the directionalities. So I'm just going to re-sketch that volumetric element right up here. Again, getting the perspective matching up with the perspective of the original three-dimensional drawing that we started with. Then I'm going to put my axes up here again, X, Y, and Z. You always want to have a coordinate system next to your volumetric element. Okay, and then let's look at our stresses. Normal stresses first. We've got two normal stresses. They're both acting on the same face. They are both compressive, so they are going to add together to produce one overall compressive stress. Okay, so let's put one compressive stress on the back face here and a matching counteracting one on the front face. And that normal stress, because it's acting in the Z direction, is going to be labeled sigma subscript Z. And its magnitude is going to be the sum of these two stresses here. So we've got 7894 psi plus 95.5 psi. Those are going to sum to give us 7.9 something, so 8.0 KSI there. Okay, if we round it, 8.0 KSI. All right, let's look at our shear stresses now. On the back face here, we've got two shear stresses that are parallel to one another. So two shear stresses parallel on the same plane. We can combine those, but they're in opposite directions, so they're going to subtract from one another. The one that's the larger is going to be the direction of the overall shear stress. So that's tau TZ, 3056. The other one being 339. So the overall shear stress is going to be in the direction of tau TZ. So let's put that on, a shear stress downward like that. Okay, and this is tau. Now let's get the notation, the naming notation of this straight. So first subscript defines the axis that the plane that the shear stress acts on is perpendicular to. So the plane that tau acts on is perpendicular to the z-axis. So z goes in here. And then the shear stress is parallel to the y-axis. So that's the second subscript. So this shear stress is named tau zy. And its magnitude is going to be 3056 subtract 339.5. Okay. So what is that? What does that give us? That gives us 2.7 KSI there. Okay. So the only other thing we need to do is remember shear stresses always occur in sets of 4, so we need to put the other ones on. So shear stress on the front to balance that out, and then a shear stress on the top and a bottom, the complementary pair of shear stresses to provide the action against that element rotating. Okay, so this picture with these two stresses, with those magnitudes, that's the answer to the problem. So now this is the fully defined stress state that occurs at point A, right? We can see all the stresses that occur at point A. All right, questions about that one before we move on to the next problem? None? Okay. That's great. So we're going to do another one that's much the same as this one, just so that you see how this process gets repeated and you get sort of accustomed to the systematic nature of the way you move through these problems. Because doing these problems is, there's really nothing new, but it's just all about staying organized so that you've got work that is of sufficient organization that you can actually figure out which stresses should be combined with which other stresses. All right. Let's erase this and get the second problem up onto the board then. Are you based in Halifax right now? You're in the Bahamas. Nice, nice. Oh, how is it in the Bahamas today? It's a nice day. Yeah. Well, we're actually having an unseasonably warm day in Halifax today. It is 15 degrees outside and sunny, and I think the normal daytime highs at this point in November are only about 8 or 9 degrees. So, yeah. Well, we did have some snow on was it Tuesday maybe? Or Monday. No, it was Tuesday. Yeah. Yeah, it was Tuesday. Yeah, it was very white outside. It was funny because it's not usually really snowy when the leaves are still on the trees. So it looked really weird having the leaves still on the trees, but the trees covered in snow too. Yeah, they're pretty much down now after the snow, and then it was a cold night that night. So and then now it's a bit of a windy day today. So even though it's warm, so most of the leaves are down now. Okay. Yeah, nice. Well, enjoy that nice warm Bahamas weather while you can. Okay, so in this question, we've got a pipe with a 90-degree bend in it, like that. Go And there's the end of it there, and then it's fixed again on that end. And we have some forces, or one force actually, being applied right to the top of the pipe at the end here. And I'm just going to sketch out that plane that the force is acting in. It's going to be acting in that direction. They're 60 degrees up from the horizontal with a magnitude of 50 pounds. And we are interested in a point that is located in the cross section. And this is actually a hollow pipe. So I'm going to draw the cross section as inner and outer diameter there. And the point of interest is actually located on the inner surface of the pipe there. So this is our point of interest, point A. Okay. Now I'll put some, the coordinate system is already labeled here in the drawing, so I'll just put that on. And I'm going to put the coordinate system on in the section plane of point A, because we're going to cut through that to reveal the internal forces and make it a free body diagram. Now I've put the label for point A on exactly where I want to put the axis here, which isn't great. So there's the other axis coming up with that line roughly parallel to that line, and then our other axis going back this way here. So the labeling on the drawing that I'm looking at is x-axis there, y-axis there, z-axis, like that there. That makes sense according to the right-hand rule. Fingers in x, flip them up into y, thumb points towards z. Yep, checks out. Okay, so this section here, that section plane, is relative to the center of this pipe is a distance of 10 inches, and then the center of this portion of the pipe to the end, that is 12 inches there. And then if we look at the cross section of the pipe, the cross section looks like this, where we have an outer diameter of, what do we have, 2 inches, and an inner diameter of 1.5 inches. This is cross section of the pipe. Okay, and point A is located right there at the top of that cross section. Okay. So the problem statement is much like before. It says define the stress state for a volumetric element at location A. Okay. So define stress state at point A. It's funny, as the problems become longer, the problem statements become very short. Okay, so what we'll do is section plane through our point of interest, figure out our internal forces, draw our volumetric element, then go through those internal forces one by one, figuring out how they create stress at our point of interest and placing those on our volumetric element. Then we'll take all the stresses on our volumetric element and figure out how they should be combined, if they can't be combined. So section cut through our plane of interest. Okay, there we go. Turning this into a free body diagram. So now this is a cut edge there. And again, helpful, I think, to write out all the equations that we're going to apply. So some of the forces along each axis, and then some of the moments about x, some of the moments about y, some of the moments about z. And then we look at the moment equations and say, hold on, the longitudinal axis of this pipe is the x-axis. So any internal moment that occurs about the x-axis is not a moment, it is actually a torque. So this should be some of the torques about the x-axis. And all of these things are equal to 0 if this is in static equilibrium, which it is. Okay. So let's go through them one by one. So some of the forces in the x direction. This force here, if that's the y-axis, we can call this the y prime axis maybe, and this the z prime axis, just to illustrate that this force is in the yz plane. Okay, it's in a plane parallel to the yz plane. So this force is not creating, it doesn't have a component in the x direction, so there are no internal forces in the x direction. We've got 0 equals 0 right now, so we don't need to put anything in terms of an internal force in the z direction or the x direction. Y direction, yes, this has a vertical component, so we're going to need something to counteract that. That internal force is parallel to our cut section, so it's an internal shear force V subscript y. Value of Vy is going to be 50 multiplied by the sine of 60. 50 sine 60, which gives us 43.3 pounds. 43.3 pounds. All right, in the z direction, yep, we have a z component or a z prime component there, so we need to have a z component here. There we go. So this is also parallel to our cut section, so this is v subscript z, and its value will be v subscript z. In this case, it's 50 multiplied by the cosine of 60. That's an easy one because the cosine of 60 is 1/2, so we've got 25 pounds there. 25. All right, moving on to our torque about the x-axis. Do we have anything that's creating a torque about the x-axis? When I'm actually doing the internal moments torques, what I like to picture is I picture myself holding the object by the axis that I'm dealing with. So I'm dealing with the x-axis now, so I picture myself holding the pipe by the x-axis. And then I think about the force that's being applied, and if the force that's being applied would act to rotate that x-axis in my hand, then there's an internal torque or moment that's being created. If the internal force is acting to bend the axis in my hand, then there's not an internal moment or torque. So in this case, if I'm holding the pipe by the x-axis, the vertical component is going to want to rotate the x-axis in my hand in this direction. So the internal torque needs to be in the opposite direction. So we need T subscript x in that direction there. Now the horizontal component, right, if I think about holding that x-axis in my hand, again, the horizontal component of that force is acting to bend that axis in my hand, not rotate it. So that's not contributing to the torque that's about the x-axis. And that matches up, of course, with the observation that if you took the horizontal component here and projected it forward, it would intersect with the x-axis, so it wouldn't create a torque. Okay, so for the value of Tx, what we've got is the vertical component, which was our 50 sine 60. Okay, so 50 sine 60, which we know is 43.3, multiplied by a torque arm of 12 inches. 12 inches. So that gives me 519.6. And that's in units of pound inches there. All right, let's move on to MY. Okay, again, picture myself holding the object by the y-axis. The vertical component would act to bend that y-axis in my hand, so it's not creating a moment, but the horizontal component is going to want to spin the object around the y-axis, or spin the y-axis in my hand. So it's going to spin the object in this direction around the y-axis, so the internal moment needs to be in the opposite direction. So here's m subscript y. And I should put my value of tx in here too. 119.6. Okay, my, let's see, m subscript y is equal to the horizontal component, which was 50 multiplied by cosine of 60. Not sine, cosine. 50 cosine 60 multiplied by 10 inches. We said that was 25 multiplied by 10, 250 pound inches here. And then we've got m subscript z to deal with now, 250. Let's put that up here at 250. M subscript z, the z prime component of 50 is parallel to the z-axis, so it doesn't create a moment, but the vertical component will act to rotate the whole thing under the z-axis, so we need a moment in the opposite direction, m subscript z, acting like that. So that's the vertical component, 50 sine 60, multiplied by the moment arm of 10 inches, and that's 43.3 by 10, 433 pound inches there. Okay, great. So that's the statics part done. So now we want to draw the volumetric element and put the coordinate system next to it. So again, when you're drawing your volumetric element, try and draw it in the same perspective as your overall three-dimensional drawing, which means that all of the straight lines should match the straight lines for your axes. So we want to have a volumetric element that looks something like this. There we go. Okay, and now the section plane of the element that's in the section, or the face of the element that's in the section plane of our cut, is this left-hand face here, right? And it's always important to identify that because, so in section plane, right? Always important to identify that face because that's the face that you place the stresses on as you find them, okay? So our coordinate system here, we've got X, we've got Y, we've got Z. So now let's go through those internal forces torques one by one, figuring out whether they cause stress, placing those stresses, calculating magnitudes. Very good. So starting with forces in the X direction, what do we have for forces in the X direction? No internal forces in the X direction. Forces in the Y direction, we've got an internal shear force. So let's look at that here by looking back through the cross section, and we've got the z-axis coming out like that, and the internal diameter, there it is, the y-axis going upwards. Point A is at this location there, and the directionality of Vy, it's acting upwards. So we've got Vy acting like that. Okay. So Vy, that's going to create an internal shear stress. To think about the shear stress at point A, right, you want to draw a line passing through point A that is perpendicular to the direction of your internal shear force. Okay, and then your area A prime is the area above or below that line. So there's your area A prime there. Okay, the shear stresses on this line are going to be oriented in the direction of Vy. Okay, so what you want to do here is you want to place a shear stress in the positive y direction. Okay, so go to your face of your element that's in the section plane and place a shear stress in the positive y direction. So this is upwards like this. Okay, now before you make a mess of your notes, just watch what happens in this case with this shear stress. This is something that you wouldn't think about until you saw it for the first time. So because I've placed a shear stress on that left-hand face, I need to have an equal and opposite shear stress on the right-hand face. And then again, those shear stresses are going to create a force couple that acts to rotate the element about the z-axis. So I need to have an equal and opposite couple to create an opposite tendency to rotate the element about the z-axis, so it's balanced in static equilibrium. So I need a shear stress on the top face like that, and a shear stress on the bottom face like that, my complementary pair of shear stresses. Now, this is a problem because of how this element is actually located in the object. So the element is actually located on the inner surface, okay? Which means that for my drawing here, the bottom face of this element, so the bottom face here, that face is touching air. That's on the inside surface, and the rest of the element projects upwards into the body. So if I drew a two-dimensional view of the element, it would be like this, where the bottom face of the element is touching air. Because that bottom face of the element is touching air, there is nothing to actually support that shear stress. The shear stress can't exist. It can't be applied to that face because there's nothing to apply it. So if the face is touching air, it has to be stress-free, and that can't exist, which means for static equilibrium to exist, this stress can't exist. And if that complementary pair of stresses can't exist, neither can the original set of stresses either. Okay? So there's actually, at point A, due to internal shear force Vy, there's no shear stress at point A. Right? This stress vector does not exist. There is stress present at other points in the cross section at that location, but just not at point A because the complementary shear stress can't exist. So no tau from Vy at A because complementary shear stress can't exist on bottom surface. That's touching So that's something that you wouldn't catch the first time you were doing a problem like this. But now you can see the importance of when you place a stress on one surface to place the other stresses that need to exist to balance that out in static equilibrium, and consider whether or not those can actually exist on the surfaces that you're placing them. All right, so we did the X and the Y. Now we're on to the Z. So let's draw the same sort of picture here. Okay, here's our cross section with the Z axis going out this way, the Y axis coming up like this. Point A is located right there, and in this case, we're considering VZ, and that shear force is acting over along the positive Z direction like this. So when we're thinking about the shear stress at A now, we're drawing a line that's perpendicular to the direction of VZ passing through point A. So shear stress is going to exist on these two lines that I've drawn. It's going to be oriented in the direction of VZ. That's not great for being in the direction that's actually parallel to the Z axis there. Do a better job. Right, so all those share the same value, tau VZ. So at point A, there's a shear stress, tau VZ, that points in the positive Z direction. So go to your face, positive Z direction, place a shear stress that is in that direction on that left-hand face. And then again, let's place the other shear stresses that have to be there. One shear stress on the back face, okay? That's around the right-hand face. That shear stress is fine because we've got a material-to-material connection between this small element and the next one that exists, and then we need a shear stress like this and a shear stress like this. And again, those are both fine because those shear stresses occur along that edge where there's a material-material connection and that edge where there's a material-to-material connection. So all fine. So this one here is getting labeled tau VZ. Okay, let's calculate what the value is. So tau VZ is going to be given by VQ over IT. For our area A prime for Q, you want the area above or below or on one side or the other side of the line that we're calculating as shear stress along. So here we go. That's our A prime there. And then for Y bar prime, we want the distance between the centroid of A prime. Centroid of A prime looks like it would be somewhere around there, and the centroid of the whole cross section like this. So this distance is Y bar prime. Now for Y bar prime, that's not that easy to calculate because you need the centroid location of sort of a rainbow shape. What you can do is, again, use the fact that you can take Q as the summation of individual Q values, and that's helpful because you know now what the centroid location is for a semicircle. So here you can take Q for this rainbow shape. Do a better sketch here. Okay. We want the Q value of that. So we can say that this is equal to the Q value for the whole outside piece, right? Subtract the Q value for the, don't know why I keep doing that, Q value for the gap that's missing on the inside, okay? So let's complete our equation and do that. We'll take Q for this being equal to Q for the outside minus Q for the gap region. That's supposed to be a G there for gap. All right, our internal shear force is what? We're looking at VZ. VZ was 25 pounds. 25 pounds. Curly bracket. Okay. A prime, the area of this semicircle, is pi over 8. Diameter, what do we say? 2 inches. So 2 inches squared. Okay, that is the A prime or that is the area of that shape. And then the centroid location here is 4r over 3 pi, 4d over 6 pi. So 4 times the diameter over 6 times pi. Okay, so this is, we're calling this QO, the outside. This is AO prime. And this is y bar O prime. And we're subtracting off the Q value for this gap portion. So pi over 8 diameter. We've got a diameter of 1.5 for the inner diameter. 1.5 squared. So this is what we're calling the gap, AG prime, multiplied by the centroid location, 4d over 6 pi. 4 times d over 6 pi. There we go. Y bar G prime. Close that bracket. Divide by I. Okay, for I, we've got the outside and the inside, and both of those share a common centroid location, so we can just apply simple superposition and do I as the summation of the I values outside minus inside. So pi over 64, and then outer diameter to the 4th power minus inner diameter also to the 4th power. That's not a very nice curly bracket there. There we go. And then T. T is the length of the line that you're calculating the shear stress along. So we need the length of that line plus the length of that line, because shear stress occurs along both of those two lines. So that the combined length of those lines is the outer diameter minus the inner diameter. So we've got 2 minus 1.5 for outer diameter minus inner diameter. Okay. A lot of numbers going into that equation there, and the answer coming out to be 35.9 psi. Any questions about where any of these numbers came from, or was that pretty clear? Okay. So let's put this value over here, 35.9. Perfect. And then we've done forces in X, Y, and Z. So now let's turn to our internal moments torques. So clean up a little bit more space. All right. Let's start with our x-axis. So we've got a torque about the x-axis. That's nice. Torques are always easy to deal with. I'm looking at the cross-section down the negative x-axis here. So z-axis pointing out this way, and y-axis pointing up like this, and point A being up at the top here, and our torque Tx occurring around in that direction. So there's Tx. Okay. Again, shear stress at point A is going to be oriented tangent to that inner circumference in this instance, and in the direction of Tx. So this is tau Tx. So that is a shear stress that's oriented in the negative z direction. So go back over here. Here's the z-axis, shear stress in the negative z direction. Okay, this is tau tx. Tau tx. Okay, and then we need our other ones. So if we have shear stress like that, we need one on that surface and one down like this and another one like that. Okay, well, let's figure out what the magnitude is. Tau tx is going to be T rho over J is equal to our internal torque Tx was 519.6 pound-inches, 519.6 pound-inches multiplied by distance rho. Now, don't forget that distance rho is the distance that your point of interest is away from the axis that the torque's acting about. So this is the inner radius in this case, which is half of 1.5.75, so 0.75. And then J for a pipe or hollow tube or hollow shaft is going to be pi over 2 outer radius to the 4th power minus inner radius to the 4th power. Pi over 2 outer radius to the 4th power minus inner radius to the 4th power. And that comes out to be 362.9. 362.9 psi. All right. Y-axis. Now, let's do the y-axis. So we have a moment my. So the moment about the y-axis, again, if you're dealing with something that occurs about the y-axis, it's helpful to draw a picture looking down the y-axis, I think. So do my drawing like this, where we've got the x-axis coming out in that direction and the z-axis in that direction there, and point A is right in the middle there, and the direction of my is around like this, m subscript y. So my, gonna push this side of the cross section in, pull that side out in tension, linear transition between that tensile and compressive stress. Point A, no normal stress from my because point A lies on the neutral axis of bending of my. From my. So no normal stress at A from my because it's on the neutral axis of bending. So we've only got one more to do, thank goodness. And that is the moment about the z-axis. And there it is, mz right here. So if we look, I'm going to look down the z-axis that way. Okay, then we've got the y-axis going upwards. We've got the x-axis coming out like that. And point A is sort of right about there. I'm just thinking about where I want to put my label. Point A is right about there. Okay, it's on the, if I drew a hidden line for the inner diameter or the inner edges, inner surface, they'd be like that. And then my moment mz is occurring about the z-axis, which is coming out of the glass right there, in that direction. So mz is taking this side of the cross section and pushing it in, taking this side and pulling it out, and then there's a nice linear transition between the two. So at point A, what do we have? We have a tensile normal stress sigma mz. So we want to put a tensile normal stress on our element. I'll put it on over here. So we're going to have a stress that's oriented perpendicular to that surface, pulling outwards from it, and then an equal and opposite one on that side. So this one is sigma mz. Okay, let's calculate its value. That's easy to do. Sigma mz is going to be given by the equation my over I, where our internal moment is mz, which has a magnitude of 433 pound-inches. Distance y, the distance that the point of interest is away from the centroidal axis that the moment's acting about. So that's the, in this case, distance, oh, I shouldn't have drawn y bar, it's just distance y. Distance y is the internal radius, so 0.75 divided by I, again, pi over 64 d to the fourth, but here we've got outer diameter minus inner diameter. So outer diameter to the fourth power, 2 to the 4, minus inner diameter, 1.5 to the 4. And that gave me, when I calculated it, 604.9 psi. 604.9 psi. Okay. So now we've made it all the way through our internal forces, torques, moments, and we can look at this volumetric element and combine those stresses that can be combined, and then provide the sketch of our answer with the combined stresses, with the appropriate labels and magnitudes as our answer to the problem. So I'm going to re-sketch the element. There we go. And put the coordinate system in. And we had x, y, z, like that. And then let's go back to our element. We've only got one normal stress, so that's easy to deal with. So that is a tensile normal stress. So here we go. So we just copy that normal stress right back over. If, let's say I want to label this one, it's a normal stress in the x direction. So this is sigma subscript x, and it equals exactly this value, 604.9 psi. So there we go. Now we've got two shear stresses. They're parallel to each other, so they can be combined, and pointing in different directions though, so we want to take the difference. The one with the larger magnitude is the overall directionality of the shear stress that we want to include on our pictures. So that's in the direction of tau tx, which is the negative z direction. There we go. Let's put in the other shear stresses we need to put in. Okay. And let's say that I want to label that shear stress right there, tau. That face of the element is perpendicular to the z-axis. So it's tau z as the first subscript. And the second subscript, the shear stress is parallel to the x-axis, so it's tau zx. And the value is 362.9 subtract, what, 35.9. Okay, so that gives us what? 327 psi. There. Okay, so we've got the combined stresses. We've got the stresses appropriately labeled. We've got the magnitudes. that's the answer to the problem. That picture, those numbers. Okay. So again, that was very similar to the previous problem, but gives you again an idea of how to work through those systematically in a way that helps you to hopefully stay organized. All right, we don't need this anymore. Just erase this. Okay, erase this, and then we'll do the third and final problem that I picked up. So the third one's a bit different in that now we're trying to get you thinking about how to do a problem involving combined loading when you're not given a particular point that you're told to look at. Okay, so in this problem, we have a mass that is being hung off a C-shaped hanger. So here we go. So this is a support point up here, and our load force F is being applied downward like this. Okay. Now let's put in some dimensions. So between here and the center is a distance of 1.5 feet. And this is going to be a piece of bent cylindrical rod with a diameter of 1 inch. Okay, so the cross section of the hanger looks like this. It's just a circle. Solid cylindrical rod, diameter of 1 inch. Okay, so the question statement says this. A C-shaped hanger has a radius of 1 inch. Oh, I'm sorry, diameter of 2 inches. Okay. C-shaped hanger has a radius of 1 inch and is made from stainless 304 steel. If a safety factor of 3.5 is required, what is the maximum allowable load that the hanger should be used for? Consider normal stress only. Okay. So this is 304 stainless. Okay, and the question is for safety factor of 3.5, max value of our applied load F is the question mark, or actually let's change that. Max for safety factor of 3.5, max value of F considering normal stress only. There we go, question mark. Okay. So what's the maximum value of F for a safety factor of 3.5 if we only consider normal stress? All right, so let's think about what we want to do to actually solve the problem. So we have stainless 304 steel and a safety factor of 3.5. So we know the allowable stress is going to be given by the yield stress of 304 stainless steel divided by our safety factor. Okay. And then what we want to do is equate this to the maximum normal stress that is present in this object. And we know that the maximum normal stress present we can express in terms of the weight F. Okay. So that would allow us to solve the problem, taking the allowable stress, equating it to the maximum stress. So then the question really becomes, well, what is the maximum stress within that object? And then looking at the object, the question is where is the maximum stress? So this is where we're taking the problems to the next level now, where you're not told to, for example, analyze the object at point A. You're not given a point at all, and you're tasked with figuring out where the maximum stress would be. So when you face a problem like this, what you want to do is just take some section cuts at some different locations and look at what the internal forces, moments, torques are, and think about how those would create stress and how the stresses at various different locations would compare. So let's do a few section cuts and experiment with this. So if we did a section cut at that location there, what would we have? We would have a free body diagram that looked like this, where we had load F, and balancing load F out would be a normal force that we need to equal force F. And in terms of stress, we've got a tensile normal force, so every point in this cross section would be experiencing a tensile normal stress sigma. Okay. So that's all we need to do to think about that section cut at this stage. So let's move on and think about a different section cut. So we could take a section cut at this location, for example. And if we did that, right, we have our section cut like this, and the rest of our object kind of looks like this here. Rounded corner there. So we've got load F here, and then for internal forces, now we have to have some of the forces in the y equals 0, so we need to have F here again, but that force is parallel to our cut section, so now that's an internal shear force rather than an internal normal force that's balancing out the force F. This is going to create a force couple, which is going to cause this piece to rotate this way. So we need to have an internal moment, M, that would act about the centroid of the cross section to balance out the moment created by force F. This moment here, the internal moment, is going to be what? It's going to be force F multiplied by the moment arm, which is distance L in this case. So we have FL here. Now, what's this moment going to do? Well, we know what moments do. They create normal stresses, and the bottom of the cross section would be pushed in, top of the cross section would be pulled out, linear transition between the tensile stress and compressive stress there. Okay. So now we've got a moment that we know creates bending stress over the cross section. We know from doing our calculations throughout the course that normal stress due to bending moments tend to be larger than normal stress due to internal normal forces. So there's a very good chance that this normal stress here, or the maximum normal stress, which would occur at the edges, is significantly greater than the normal stress created from the normal force. So this is a better location to look for the maximum normal stress than this location over here. So let's keep going. What if we cut somewhere like that? Then we'd have a free body diagram that looks something like this, where we've got load F. Our internal normal force would have to equal F. And again, we need an internal bending moment, M, that now was equal to F times L, right? This F multiplied by this L would give us what this moment would need to be about the center of the cross section for some of the moments about that point there to be 0. And here we know L is 1.5 feet. So again, this internal moment, compression on this side, tension on this side, and a linear transition between those. So thinking about these two stresses here, okay, those two normal stresses from our bending moment M, I'll label them sigma subscript M, those are going to be larger than the normal stresses present here because L for this diagram is larger than L would be for this diagram when you keep moving that section cut over right to the corner, right? If you bring it right to the corner, that distance L is not quite equal to 1.5, whereas this L is equal to 1.5. So the moment's larger, so the normal stress is going to be larger. So this is an even better area to look for the normal stress than this is. But now, thinking about the fact that there's the maximum normal stresses due to bending at the edges of the cross section, we are also going to have normal stress on the cross section caused by the internal normal force. So if we think just about that here, we've got an internal normal force like that. So we're going to have tensile normal stress created at every location in that cross section sigma subscript n. Looking at the directions here, we've got tensile normal stress on this side, but compressive normal stress from bending at that same location. So those are going to subtract from each other, making the overall normal stress smaller. At the inside location, however, we've got a tensile normal stress from the normal force, and that's going to add to the tensile normal stress from bending. So that location here, which is the same location down here, that's the location that we want to look at for analyzing the maximum normal stress. And that location could be any point along the inner surface of that C-shaped hanger, because all these points would have a stress state that looks exactly the same as what we've drawn here for this example. So these points are all points of sigma max, or all points that experience sigma max would be a better way to say that. Okay. So let's take our equation here and just work with that. So sigma y divided by safety factor is equal to sigma max, right? And now we're saying that sigma max will really be the normal stress created from the moment plus the normal stress created by the normal force. And this is going to be my over I, and this is going to be n divided by a, sigma y divided by the safety factor on the other side. So we're in a position now where we can fill in numbers for everything. So sigma y comes from the material property tables. Let's see what it is for a stainless 304 in US units. 30 KSI. 30 KSI for stainless 304. So 30 times 10 to the 3 divided by our safety factor of 3.5 is equal to our internal moment, which is going to be F, our unknown force F, or the force that we're trying to find, multiplied by distance L, which is 1.5 feet. And then we want to change that feet into inches. So we're going to multiply by 12 because we want pound inches, PSI for equations involving stress. And I here, pi over 60 4d to the 4th power. What was our diameter? It was 2 inches. D to the 4th power. Plus our internal normal force, which is equal to F as well, divided by our cross-sectional area, pi over 4d squared. Okay. All right, and then we can solve for our unknown in that equation F, which is the maximum load that we can apply for a safety factor of 3.5. And when I did that, let's see what I got. 368.8 pounds. Now, if you're rounding this to the nearest pound, then you couldn't round this up to 369 pounds because then your safety factor would drop below 3.5. So if you were rounding to the nearest pound, this would need to go down to 368 pounds. Okay, questions about that problem there? That's great. Okay, so those are all the problems that I wanted to go through with you today. Did you have any other questions about the project or anything else to do with the course?